Just let us recall the previous topic. So if you look at it, in fact, we have done a very brief review or discussions on the different variety of classifier algorithms or machine learning algorithms, superposition, uh, supervised learning, unsupervised, and reinforcement learning are the techniques which have been already discussed in the previous class with the examples as well as some terminologies, particular terminologies have been addressed, and even application of each of the types of classifier or learning algorithms have been mentioned. Also, we have started with the next, we entered into this statistical decision theory topic. This is where we get into more generalized study of this regression and classification. So under this topic, we study about regression. In fact, when we say that it is a regression, it does not mean only the linear regression. It can be other like logistic regression, or it can be KNN, what you have, K nearest neighbor regression kind of thing. Okay, so these are the general, the mathematical foundation that we are discussing here is for the mathematical foundation for regression. Okay, that's what we just begin with here. Okay, it gives a kind of a framework. So we have started with considering our input vector. I mean input x representing here in this case input data point, which is drawn from a p-dimensional space. So if you want to represent it, say vector x that has p values in it, x1, x2, and so on, xp, right? So what exactly x1, x2, etc. represent is we call it as features, correct? Different features. X1 is one feature, x2 is another feature, and so on. Or attributes. In the previous problem, like we had seen the attributes such as what is that, age of a customer, or it can be income of a customer and things like that. So we have given the examples. Now more just p-dimensional space, right? So for p equal to 2, we know that. And what about output? Output y is drawn from a real numbers. Why so? It is because it is a regression case. So in the regression, the output is continuous valued function, and therefore y is drawn from the simple 1D real space. Now we had made certain assumptions here that in such a now we have to understand the fact that the input is input x, what you're talking about, the data points. There may be many data points, x1, x2, etc. Vector x1, vector x2, and x3, and so on. So these represents what? This represents data points, input data points. In the each will be in a p-dimensional space. Okay, so in a training data, so if you think of a training data, so what is given to us is a pair of x and y. It's something like this. For x1, okay, vector x1, there is a corresponding, there is y1. Y1 is the output. Okay, x2, there is a corresponding y2, and so on. say if there are n data points, capital N, so xn, there is a corresponding yn. This essentially represents our training data set. Okay, training data set, right? Now in such a training data set, you can understand, so this is basically representing these vectors, x1, x2, etc. Or in general, if I think of some vector x like this, what is indicated here, this x, so this is a random variable. We can understand that it is a random variable because it's drawn from the input data space, which can take a range of random values. Therefore, this vector is a random vector. Therefore, there must be a associated distribution for its quantification, right? So here, as we have seen in the training data, there is an associativity between the input data points and its corresponding output. There is a mapping that is already given to us. So the probability distribution, joint probability, is the right distribution that we can draw from the input space, and it is denoted as probability of x comma y. X represents the input vector and y represents the output. Correct? That is the assumption that that data comes from this joint probability distribution. So that's one of the assumption to go forward. Right? So our objective or goal is to learn a function f of x. Now we have to come out with a mapping function, f of x, such that it will map from a p-dimensional space to a one-dimensional real space. So here the vector x belonging to this p-dimensional space and y, which is belonging to the one-dimensional output space. So it's a mapping function from p to one dimensional, 1D, p-dimensional to one-dimensional. That's our objective. So here we are actually not particular about what form of f that it should take. What is the form of f? What's the nature of f? No, the objective is actually not that. Later we will come across that anyway. Now for the time being, we consider one form of f of x, one possible form of f of x, which is linear, in which case it results in a linear regression. The mapping f of x such that it is mapping from p-dimensional to one-dimensional. So this mapping function can take any form, and one of the such forms is this. So if f of x is a straight line, or rather a plane, or I can say hyperplane, okay, so in p-dimensional space, so then we can predict y as something of this sort. It's a linear combination of the input features. So these coefficients betas, actually represents the straight line, or whatever you call it as hyperplane. Okay, so here the goal is to come out once the nature of f is given. So what is the nature of f here, or the form of f? It is a straight line. So once the form of line is form of the function f is given, then next thing is to calculate or to come out with the betas, beta 0, beta 1, beta 2, and so on, so that we have designed the regressor. Okay. Now this y cap here, it is denoted, it is meaning that it is the uh, estimate of y. Actual y is different. You understand that? So for given x1, so we have, for given x1 vector, there is a given, there is a corresponding y1, is it not? Similarly, x2, y2, and so on. Now there exists some x query point for which the corresponding output, so we are denoting it as y or y cap rather, which may not be the actual y, which it's supposed to be true y. We call it as an estimate, which is obtained as the output of this function, right? That's how we interpret it as. So f of x, if you look at, it's a linear expression that you can see, can be written as a summation here, or this expression, that is y cap is equal to beta 0 plus summation k equal to 1 to p bk into xk, can be simplified, or in a single summation we can represent it better as k, from letting k to run from 0 to p by including x0 also into this summation with the condition that x0 is equal to 1. So this essentially represents the linear regression. I hope this point is pretty clear to us. So there is one of the form that the possible form that f of x can take, or the function f can take, correct? Next we have took examples of another one more classifier, knn, or the nearest neighbor classifier. So we wrote the expression here, we have the expression here, that is f of x, that is y cap is equal to f of x is equal to 1 by k summation of yi, such that it's for those i's with xi belonging to n of x. Here n of x represents the neighborhood of x. Okay, it represents a neighborhood of x. So you are considering those xi's, we are considering those xi's which are in the neighborhood of x, and we are considering k is the number of neighborhoods. There are k represents the number of neighborhood of neighbors of the x, right? So if there are k equal to 3, we have to consider 3 neighbors of this x, query point x. So I here essentially for x1, x2, and x3, so 3 neighbors we are supposed to consider. Now we'll take this example for better clarity. So n of x, I said the neighbors of x, and k is the number of nearest neighbors that are considered. Okay, so there is a distribution of the data that we have. Let's consider some x1, x2, etc. are in the space. These are the input data points. Now there is a query point here. Just let me highlight this. The one, if you can see it in the red color. So this represents what a query point. So we know already for x2 it is y2 and so on. Okay. Now we have another query point, new point, which is a query point whose output need to be computed. So what we do in knn is we find out the nearest neighbor. Suppose that k is equal to 3. We have considered k is equal to 3. So we know the outputs corresponding to those 3 nearest neighbors. Here it happens to be like x2, x3, the data point x3 and x4 are nearer to the query point x than compared to the others. Okay. Though, so we may consider S2, X2, X3, and X4 are the three neighbors. And the corresponding outputs are Y2, Y3, and Y4. So what we do here is we assign the output of this query point as the average of these Y2, Y3, and Y4. That is the estimate. That's what exactly is done. So you pick, we pick Y2, Y3, and Y4 correspondingly our output to the nearest neighbor, and find the average. The average of Y2, Y3, and Y4, therefore, is the value of the function at corresponding to X. So this is called as a nearest neighbor example that we have. In fact, there are different ways, it is not the only functions, the linear regression or k nearest neighbor regression. No, there are many functions that we have. This is just an example to, understand about the regression concept. Now, there are different ways in which, the mapping function can be defined. Of course, that's what I've been telling. But there is a assumption on the form of f. You have to understand here the bias. So bias is that the form of f that we assume. So if you assume that it is linear, a kind of bias that we have made, that it is linear. Okay. So if you otherwise, our actually the objective is to come out with the function f without assuming any, f taking any particular form, without an assumption on the f. Okay. Then how do you choose the function f is the question. So there are, it's a challenging actually the question to answer, because there are different forms the f can have, many forms that f can have, and which one that you choose, which is you say that best for my input data. And suppose say you have chosen a particular suppose say one particular say linear regression, one particular form of the the form for f of x. Then how do you find out the corresponding coefficients of that? Suppose say you have, suppose you choose f to be linear, then how do you find beta? That is the next question. Having chosen particular values, chosen particular function, then how do you obtain the coefficients? So this has to be addressed, correct? So there could be many different ways, of course, in which beta can be defined. There are different ways in which we can achieve that. And again, to choose or to estimate the beta for a chosen model, that's also an issue which has to be addressed. We will address that. And there are different, we require what is known as a measure, metric. We call it as a performance measure. So to address that, first we have to define ourselves and make it clear what is our performance measure. Performance measure is also, we call it as a loss function. Loss function. The loss function actually, it compares the predicted output with the true output. So here f of x denotes the predicted output, and y is the true output. A predicted output or estimate, or you can call it as estimate. Okay, you can call it as estimate. So what loss function does, it compares these two, y and f of x, and gives comes out with, I mean, a certain value which is called as a, generates a error value. Okay, so now the goal is to find a function f of x, very clear, such that the loss function is minimized. So here very clearly the goal is to find uh, you know f of x, that is a function f of s, find f such that L is minimized, loss function is minimized, is it not? So our objective is to come out with the function, mapping function. So objective is to come out with the mapping function such that the L, this has to be reduced, or I mean minimized, for all possible values of x, input values. That's how we come out with the. So we are not really worried about the shape or the form of f that it takes. We are not worried about the form or particular shape. We are worried about this only. So we have set up a particular performance measure, and based on that performance measure, like a loss function, so the objective is to minimize. I hope that's pretty clear. So having said that, now what is the loss function that we consider? So there are many different loss functions possible, out of which the most popular or well-known loss function is the squared error. Okay, which is simply the square of the difference between the of course true output and the predicted output. True output and the predicted output. So squared error is equal to y minus f of x the whole square. Hope that is pretty clear. The prediction error of a function f can be quantified by also using mean square error. This also further you can quantify it by MSC, or it's commonly known as expected prediction error, EPE, of a function f. Here EPE, it's not a function of f, but rather it's the EPE of the function f. Hope that difference is clear. So this is nothing but expectation of this squared error. So we have the squared error here. So if you take an expectation of the squared error, that gives the what is known as expected prediction error. So this is a measure that we can have, or performance measure that we can have. Expectation has come from the fact that these variables are random variables, right? The input, as I already mentioned, it's represented by the set of random variables. So therefore, if you want to evaluate this, then we require the knowledge of the underlying distribution that we have, because we have an expectation here. As per the definition of expectation, it is the integration of this into the underlying distribution, is not? So the distribution we need to know, right? So here, as I mentioned earlier, we have assumed that the data comes from the input data set. It's come from the joint probability distribution, that is probability of x comma y. Correct? Input and output. So this is that from the training data set we get the joint distribution, and the PR of x comma y is representing the joint probability of x and y. So using this, we can expand, you can write the expansion for this expectation by using the definition of expectation, that is the integration. And can write it as integration actually from minus infinity to plus infinity. The variable under consideration here, it is y minus f of x the whole square into this essentially is the joint PDF. This must represent the joint PDF of x and y, isn't it? Joint PDF of x and y. So therefore it is denoted something like dx dy. We can also use in the standard fxy kind of thing, but f is already used for the function mapping function here. So this is the equation 3 what is shown here. So that is an expanded version of equation 2. Hope that's clear from our knowledge of probability and random process. Fine. Now further, to get into the details of rather interpretations, rather to know how the model behaves in a variety of scenarios, we need to get into the details about the joint PDF of x and y, or rather probability joint distribution, joint probability of x and y. That is, from our basics of product rule of probability, we can always write probability of x comma y can be written as conditional probability of y given x into probability of x. Correct? So what it tells actually, this tells that there is some chance with which we choose the point x, and then probability of seeing a particular output for a chosen input x, probability of finding the output y for a chosen input x. So this actually helps us in modeling the function in a variety of scenarios, situations, right? So this is something which we can draw from the data set, from the input training data set. It is a conditional probability of output given the input, okay, given a particular input. Hope that point is clear there. Now, one of the advantage of having this conditional probability is that suppose there is a noise in your data, suppose say, then for some extent it can be handled by using this conditional probability. That is, p of x comma y helps to know the model in different scenarios I said. So if there is a noise in the measurement, then it can be addressed by this. It is like, suppose say you are measuring a temperature in a day, and particular time, suppose say in during something like say 12 p.m. suppose say you have noted down the temperature, okay, it is as some 60 degree or something, say for real value, let me consider something like say 35 degree or so, maybe depending on, of course, locality. This may not be the true case. There may be some noise in the data, because usual value that say at night it is PM, or rather it is AM, right? Yeah, fine, sorry. So it takes maybe something like 20 degree. That is the usual case. Maybe it may be in and around that particular case. And when there is a drastic change of values for a particular input, so this can be very nicely addressed by the conditional probability, that most of the values takes this value, that is around 20 degrees centigrade. Okay. Now the only particular input, only one particular input is taking something else. So this can be addressed like what is the probability of y for a given x. So this actually addresses such a noisy case. Hope I am trying to explain the noise measurement, okay, how probability can be addressed. Another point is about the lack of knowledge about the system itself, or the ignorance about the system. Suppose you have taken, in the same case, you have taken the temperature measurement is correct, but the measurement has been done in something like AC room. You have taken an AC room measurement of a temperature, okay, and it records something like say 19 or say 15 degrees, something like this, whatever. So this is actually not the correct measurement. It is not, the measurement is correct. The measurement that has been taken is correct, but it's not taken in the right place, or it is to do with the system. Okay. So in such a case, again, this helps, the probability of y comma x helps in addressing such problems. So in associated data, there can be different types of noises. There are, one noise, where you cannot measure, okay, and another case where you can measure, measurement is correct, but it is wrongly measured because of the system, or the lack of knowledge about the, or the ignorance about the system or the model. Okay, hope that point I was talking about, that is about the probability of y given x. Why that is important, that's I was addressing. Okay, now coming back to the equation 3. Look at this equation 3. This has got two things here. When I say joint probability, joint PDF, so it's a product of, you can write the joint probability in terms of the conditional into p of x, simple probability of the input space, input data. So therefore this itself can be divided into two parts. One is a conditional, one is simple probability, and then we can express EPF in terms of the product of two expectations. One is expectation of y given x, that's coming due to this. Okay, another is due to this is expectation of x. So this, therefore, equation 3, whatever we have seen, that can be rewritten like this. That is expected probability of error of a function f. So it is Ex, that is expectation of x, into conditional expectation of y given x. Conditional expectation of y given x, of course, of y minus f of x the whole square given x. Hope this point is clear. This is actually, we are writing it from the previous expression by using the this product, probability rule that we had. Okay, product rule. Okay, fine. Return this. Now what exactly this equation 4 represents is the error expected error, probability of error, is not. Our objective goal is to minimize the error, right? Okay, so in order to find the function, so we have to minimize this for a given value of x, and we have to do it for all possible. The EPF of x for a given value of x. Note that it is for a given value of x. the uncertainty so is therefore over the value of y. Uncertainty lies on the value of y. What is the expected value of y given the x? Hope that point is clear. So the error is found after conditioning. So we call it as the error is found after conditioning on the input x for the given value of x. Okay. Now, as I mentioned earlier, to find the minimum value of the prediction error by conditioning on a specific value of x, so we have to find out the function f. Okay, our objective is to choose a function f, okay, by minimizing the EPE by conditioning on a specific value of x. So here it is assumed that the function f can take all the possible values. Remember, okay, function can take all, f can take any value, take any form, rather any form. Just I am recalling this now and then. So we choose f just such that for every value of x, that is for every value of capital X equal to small x. I hope that point is clear. So we have to choose. So capital X represents the entire possible values variable, random variable. X is one of the instances of that random variable. So we choose the function f such that for every value of x, it makes the best possible prediction. That should be our objective. So how do we choose f? So we go for argument minimum of this function, that is equation 4. If you look at the equation 4, objective is to minimize argument minimum, which is minimizing the RHS of this. Okay, so minimizing RHS with respect to what? With respect to f of x. So in the RHS, if you look at, there is actually argument minimum of, you have ex and ey given x, expectation of x and expectation of y given x, isn't it? But here we are considering only expectation of y given x, because this expectation of x is nothing to, there is when it comes to minimization, there is no role to play because there is no conditions on x or condition on y, right? Y given x, that is there only for this. Therefore, so this equation can be written as equation 5 given here. Please note that this argument minimum, so is with respect to c, a variable, or rather another term that we have is a c here. Here c is exactly, it's a value of f of x, that is at a particular value input x, f of x is equal to c. So it's output at a particular value of the input c, that is for a given input x, for a given value x. Okay, f of x gives the specific value. That specific value we denote it as c. So the objective is to find the error y minus y. Error is true output minus the expected output, I mean estimate of the output, predicted output c, that is f of x. So the difference between that, square of the difference, so that is error, must be as small as possible. Okay, so the in equation 5 here, so the minimizing is done over the different possible values of c. Please observe that it is not for a single values of c, for all possible values of C, done over the different possible values of C, that can be assigned for f of x. Okay, so we pick that value of C which gives the smallest error. You choose that value of C which gives the smallest error. So there may be different scenarios in which x, for different values of x, it gives a C as output, and you choose that value of C which gives the smallest error. I hope that is the argument function. So the argument minimum function first minimizes with respect to C. Okay, if it minimizes, finds a minimum function, minimizes with respect to C, and takes that argument which achieves this minimum, which achieves that minimum. So it is done for all possible values of x here, small x, in capital X, so that we will get a function f of x. So this is the just explanation which I am trying to give for estimating the function, mapping function f, okay, in any regression problem. So again I repeat, here the functional form of f is not assumed, and there may be a possible, because of this, because we have not assumed the functional form, there may be a possible overfitting. Okay, that problem may be there. Okay, these points I think I have said. Pick that C which gives the smallest. Okay, fine. Now coming to the finding the value of C, if you look at it, look at the previous expression, equation 5 here, same equation, argument minimum on C. So if you're thinking of finding the value or the procedure for finding the value of C, so in equation 5, this equation, there must be a single value for C. Correct? That's what I have been explaining. Single value for C, only one value for C. Say you have, suppose say there are three measurements like y1, y2, y3. There are three measurements you have made. For input x. I'm trying to explain this procedure. I mean, how to choose the value of value of C. So there are measurements that multiple times. Suppose say we have made measurements at multiple times, and we have got y1 as first time when you measure for the input, we got it as y1. Second time when you measure for the input, you got it y2, and third time it is y3. Correct? Then which measurement, then how to take, then it's required to predict the output for the given input x. So the best thing to do is take the average, because the quantity that minimizes the squared error, in the previous case, the quantity that minimizes squared error in the previous equation 5 which you are discussing is the average value. So we have to assign y1 plus y2 plus y3 by 3 as the corresponding y. Correct? Therefore, it is average is basically representing the expectation for a random variable. Average means expectation, right? So therefore, function f of x can be written as, it is expectation of y given x for a particular x is equal to x, y given x is equal to x, and do it for all values of x, you will get a function f of x, right? So that's equation 6 is very powerful, and it describes the what is known as conditional expectation, or it is also called as a regression function. So we call it as a regression function. Equation 6. Okay, any questions so far? So we have just arrived at a regression function here. We'll get into some limitations of this anyway. And 1 second. Yeah, any questions so far? No, right? Yeah. Fine. So we have come out with this equation 6 representing the regression function. Right. Now, one thing we have to note down a few points here, that this we are talking about this probability, conditional probability. But conditional probability, the actual conditional probability is not known, and it has to be drawn from the training data set. This is a point that we have to note. Therefore, depending on the data set that we have, training data set that we have, this estimate would be. How better this will be, that depends on what is your training data set that you have. So in fact, this conditional expectation is in turn depends on the data set. Okay. Of course, we can determine from the data set, but the question is whether this determined conditional probability, how far it is representing it. Okay. So one possible way to find this is to take the average of all the output corresponding to the data point x. So like what we did earlier, like here again f cap, it is given. The notation here is that it indicates it is the estimate of f, not the true f. True function is different from the expected, or rather estimate, or what is the probability of that. Okay. So f cap of x can be obtained from this same conditional probability only, but it is the average of those. Correct. That's the one of the way that we can obtain. Also, it is not able to make a prediction of any data point which is not present in the input data space. You take some x dash and try to predict. So it is not possible to predict that because it is not there in the input space, right? So if there are not enough measurements at the input side, then it's difficult to find the or predict. Then in that case also, this equation 7 will play the role of that. I mean, it will overcome the problem of that. That is, the average will be taken, but average need not be good always. Average may be poor, and estimate of expectation for much cases, some cases may fail. Okay. But this is one of the possibility that you can take the average also. Okay. Another way to address the problem, instead of finding conditioning on a point, you condition on a region. See, in the previous equation, you see that everywhere it is conditioned on a point. Expect how the regression function is defined as, it is expectation of y given x . So in order to avoid the problem of that data availability or the data set, so one way to address the limitation is to relax on conditioning here. Instead of conditioning on a point, you try to go for condition on a region, correct? So we know, so there is a query point x, suppose say, and in fact, comes back to our k nearest neighbor only. So you have x1, you have x2, suppose x3, and say some x4, x5, and so on. So if I consider k equal to 3, then you have to find the average in this region. Instead of conditioning on a point, every point, what you do is now you condition on this particular region. Now that entire region is so by doing that, for that region, we assume that output is constant. So that is the indirectly it is assumed. So when you do that, when you do such a relaxation on the conditioning, so what happens is, whatever the query point you consider in that particular region, you see that its output is constant. The output is same, is it not? So that is in the neighborhood of x. Okay, so any that depends on k, can be any value possible. Maybe this example I will consider here. Okay, it's an example of a one-dimensional data, maybe a temperature data. Okay, so here look at the query points x1, x2, etc., x7. These are the data points. These are the input data points. And what is the corresponding data output? That is y1, y2, and so on, marked in the red very clearly. So these are the output. It's known from the training data set. There is a query point here. There is a query point. You can note a query point here, x. Okay. Now our interest is to find the output for a given this x. Okay. Now pick k nearest. Say k equal to 3. Let me consider k equal to 3 here. Okay. In that case, in this example, x3, x4, and x5 are the three nearest neighbors of x. Hope that is clear. x3, x4, and x5 are the three nearest neighbors, and the corresponding output is y3, y4, and y5. So what we do here, we consider the average, that is y3 plus y4 plus y5 divided by 3, is it not? So that may be somewhere here. Suppose this value is here, this is here, and this is here, some average somewhere here. Suppose say this is the average point. Let me represent this by this color. Okay, but it's interesting to know that even if you move this query point to the left or right with a certain extent within a marginal certain region, this point will be same, because in those region the nearest neighbor is nearest neighbor for this query point x in that region is the same as x3, x4, and x5. Of course, there is a certain region. Beyond that, some other points will come into picture. So what I'm trying to say is, you observe that the output is constant in that region. Hope you are getting the point there. Okay, observe that the output for query point in a certain region, is the same, that is constant. So in this region, k nearest neighbor will remain the same points. Okay, so nearest neighbor does not change. That's the meaning. So essentially, the assumption made is that the output is consistent over a region. So output is consistent over a region. So we can say that the above representation, we get a KNN from the previous regression equation just by minimizing the expectation. That is, how we have obtained, we obtained the classifier just by taking the consideration of this. See, look at this, relaxing relaxing on the condition that instead of taking a point, we have now considered the region. Just by relaxing the conditioning, so we have obtained the k nearest neighbor. Hope you can make that statement. Okay. If there is any questions, you can stop me, no problem. Okay, just let me further continue. It's, what's the time now? It's okay, almost 3. Let me take another 5 minutes or so. Let me complete this part. Okay. Okay. So we can say that the above representation is nearest neighbor classifier, which implies minimizing the expected prediction error yields the nearest neighbor classifier. This is what I said. Minimizing the expected prediction error yields a nearest classifier. Okay. In a way, we can make this statement anyway. So now KNN, of course, is a powerful classifier, and the estimate becomes more stable. I would say the estimate becomes more stable as this k increases. K tends to infinity. Both k and n, of course, has to tend to infinity, where n represents, capital N represents the number of data points in the input, and k represents the number of neighbors that you are considering. Number of neighbors, and n represents the number of data points, input data points. So as and when the input data points increases, tends to infinity. So for the larger values of k, you would see that there is a stability. That means, so f f cap indicates what? It is a prediction, or the what we call estimate. So estimate of f of x approaches f of x. So f cap of x approaches f of x when n comma k tends to infinity. That is what we are trying to say. Okay, right. Coming to the certain limitations. Now, in the previous assumption that n tends to infinity is not actually practical, because we don't have infinite data set in any given problem, and the dimensionality of the input data space as it increases, this is a point, important point actually, the dimensionality of the input data space. So if it increases, then the data becomes more sparse. That means there is a lot of vacant space that is being created because of the dimensionality, increase in the dimensionality of the input data space. If a p-dimensional data space with the p large, then you understand that the data which are spaced in the in that dimension will be sitting apart. There will be a lot of vacancy in that volume or in that space, right? So the output may not be constant over the such a large area. So if you are going for making an average in such a large volume data, so your constant may not represent actually the output. Okay, you are making a average on a different classes or different types of data you are making average. Okay, so that may not represent. So in such cases, a certain amount of bias on function f is required. So the moment when you say that you assume a function f of x, that means there is a certain kind of a bias on the mapping function. Okay, so if you consider a regression case and you consider f is linear, then that is a bias that you are going to do. If you consider that it is a knn, then that is the bias that you are going to have, right? So there is a certain, in some cases there is certain amount of bias required, but too much of bias also leads to the problem. Okay, so this is about the overall, statistical theory that we have discussed under the regression, and we will consider a particular case of linear regression again. Okay, so we'll go ahead with the linear regression next anyway, so that maybe I will discuss in the next class probably. So linear regression, actually we have to bring a notion of matrix, and we need to compute now these coefficients b0, b1, b2, etc. This has to be computed by using some criteria, minimization criteria, the loss function. We have to take certain loss function, and then using those loss function we have to compute the beta. So those things we shall do it in the maybe next class. Okay, any questions so far?
Excuse me, sir.
Yeah, please. Yeah, please.
Sir, when you said some bias is required in the data, like I didn't exactly get what you meant.
Yeah, when we are talking about a bias, the bias is actually, what do you mean by a bias? We have to see. Bias is, so I'm talking about inductive bias. Inductive bias. So I was talking the other day that the bias can be a language bias, language or search bias. So when I talk about inductive bias, it can be like you are fixing on a function f. In the earlier discussion, in the very beginning, here and there I used to tell that f can take any form. We used to say f, let the f can take any form. That means there is no bias on f. But if you say that f is linear, then you are limiting your f to that linearity. If you say that f is basically does the averaging operation. So that's the kind of bias that we are going to introduce. Okay, that's what I said about the biasing. Am I
Yes, sir.
trying to
Thank you,
address
sir.
your question?
Understood.
Yeah.
Yes, sir. Yes, I got it. I got it.
So any other query you have? I'll just download the attendance in the meantime.